Hello, and welcome back to Physics 141, Classical Electromagnetism 1. We are still on the third chapter of this course, which is on electric fields in matter. So, before we proceed with this lesson, let's first review what we have discussed so far. So, we have discussed about electric dipoles in the previous chapter. So, if you have an electric dipole, it's basically just a pair of a positive and negative charge separated by distance d. And this electric dipole has what we call an electric dipole moment, which is just the product of the charge times the distance. So a polar molecule, such as the water molecule H2O, polar molecules are actually electric dipoles. So this means that one side of the molecule is positively charged and the other side is negatively charged, making it having a dipole moment. Take note, not all molecules are polar. So there are also non-polar molecules. So basically, it doesn't have a dipole moment. So for this lesson, we will be discussing what is the force acting on a dipole, including the torque on the dipole. Okay, so we mentioned earlier about a polar molecule. A polar molecule inherently has a dipole moment. Now, if you expose this polar molecule to an external electric field, so what will happen is, if you recall, positive charges will go along, will be pushed along the direction of the field, while negative charges will be pushed in the direction opposite to the field. So this means that the positive end will be pushed in this direction, along the direction of the field, while the negative end will be pushed in the opposite direction. Now, if the electric field is uniform or constant, then these two forces, the forces on the positive end and the forces on negative end, will actually cancel each other out, having a total net force of 0. But even if the total net force is 0, the torque is not necessarily 0. So this will actually make the molecule rotate in this direction, in the clockwise direction, because there's a force pulling its head in this direction to the right, and there's a force pushing or pulling its tail to the left. So the molecule will rotate, and there will be a net torque, and the net torque in this case is just the dipole moment across the electric field. So the effect of an external field on a dipole is actually acting a force and rotating the dipole in such a way that the dipole moment, so since the molecule will now rotate counterclockwise, so it will move like this until such time that in equilibrium, the dipole moment of the molecule will align with the electric field. Take note that the dot product, the magnitude of the, cross product rather, the magnitude of this cross product will be the magnitude of P, the dipole moment P, the magnitude of the electric field E, sine theta, where theta is the angle between the dipole moment and the electric field, that is theta. Now, when theta is equal to 0, meaning when the dipole moment is already aligned with the electric field, then sine of 0 is 0. There's no longer any torque. So the dipole will no longer rotate because it's now in equilibrium. So once the dipole moment is aligned with the field or with the electric field, and that happens at theta is equal to 0. Okay. However, if you have a non-uniform electric field, then the net force is not, the force exerted on the positive side will not be equal to the force exerted on the negative side, and hence you will have a net force. And in this case, the net force is given by this equation here, P dot the del operator acting on E. If P is uniform, it's just equivalent to the gradient of P dot E. But this is the general formula for any P, for any dipole moment P. Okay. In this case, the net torque will now have an additional term, which is R cross the net force. Take note that this equation will reduce to this equation if the net force is equal to 0. That is if you have a uniform electric field. So this is 0 if you have a uniform electric field, but in general, this is the net torque on a dipole. Okay. So let's have an example on dipoles. Okay, so if a dipole can rotate, it means it has a rotational kinetic energy. And rotational kinetic energy basically comes from the energy of a dipole, or the potential energy of a dipole. The potential energy is just converted into kinetic energy for the rotation. So for this example, you are asked to show the potential energy of a dipole is negative P dot E. So there's a difference here. Take note that the potential energy in terms of dimensions is actually has a similar unit to torque. So P cross E, but this is P dot E. Take note that for torque, you don't convert the unit to joule. It's just Newton meter. But for potential energy, you convert that Newton times meter into joule to signify that it is energy. So Newton meter, a unit for torque. If you combine the Newton and meter to form joule, it's now an unit of energy. I know, it's quite confusing. Okay. So show that the potential energy of dipole is negative P dot E. So I'm just gonna use my board mode so that we'll have a lot of space. So in your basic physics, you know that the work done by a conservative force is the negative change in potential energy. Therefore, in this case, the work done by the, say, electric field is just equal to the negative change in potential energy of the dipole. So, so we start with this equation here. Now, if you will recall, if this is the direction of the electric field, and this is the direction of our dipole, P, and the angle between them is theta. So the action actually of the electric field on the dipole is to force the dipole moment to align with the field. Okay, so work in terms of torque is just the torque times the differential angle, theta prime. So I will just name this as theta prime. That will not be confused later. So that is actually the work done by a torque. It's the torque times the differential angle. In this case, d theta is actually negative because this angle is decreasing. As P aligns with E, this theta prime angle will actually decrease. So this is actually d theta, the change in theta is actually negative because it's decreasing. This angle is actually decreasing as P aligns with E. So we can actually shift we can actually use negative d theta, where now theta here is our standard angle, which is increasing, an increasing angle. So in this case, this is equal to negative du. So we shift from d theta prime to negative d theta. So the negative sign is no longer will cancel on both sides of the equation, and we'll just have tau d theta. I almost forgot. We used tau for the volume in this section, in the previous section. So don't be confused with our notations. The tau here represents torque. It doesn't represent volume. We will use tau for volume if ever we are dealing with the potential, electric potential, because the symbol for electric potential is V. Hence, you cannot use the V symbol for volume. So here, torque means it's not volume, but it is torque. So tau means torque, not volume. Okay. So from our definition of torque earlier, torque is P cross E, and the magnitude of that, this is just the magnitude of torque, that's PE sine theta. So this is now the magnitude of torque, PE sine theta. Now, P sine theta, d theta, this term here, that is just the differential of cosine theta, negative differential of cosine theta, right? The derivative of cosine theta is negative sine theta. So sine theta is the negative derivative of cosine theta. So we can now have our du as negative PE, the differential of cosine theta. So if we now try to solve for the potential energy, we integrate both sides. So in this case, assuming the dipole moment magnitude and electric field magnitudes are constant, so we are just taking the integral of the differential of cosine theta. So the integral of the differential of a function is just that function. So the answer of this is just cosine theta. So we see that u will just be negative P E cosine theta. And PE cosine theta is just the definition of that product between the P vector and the E vector. So this is just negative P dot E, which is what we are trying to show. So QED, mathematician says, quite easily done. Okay, so that is the answer to our problem. Show that u is negative P dot E. Okay, I'm just gonna erase this. So let's now proceed to the next example. So for the next example, okay, it's now torque between dipoles. So we have 2 point dipoles, or so say 2 pure dipoles or point dipoles. P1, the dipole moment is directed up, and then a distance r from P1 is another pure dipole or point dipole P2, where the dipole moment is directed to the left. Sorry, to the right. My right. Also your right. So we are asked to find the torque on P2 due to P1, or the torque on P2 because of P1, and vice versa, the torque on P1 because of P2. So some of you may be wondering right now that the two torques must be the same, right? It's mutual. The P1 will act a torque on P2, and P2 will act a torque on P1, because these two dipoles have their own electric fields. But there's no such thing as the law of interactions or Newton's third law for torque. Newton's third law only applies to force, meaning the force exerted by P1 on P2 is definitely the same as the force exerted by P2 on P1. But the torque is not necessarily the same. Okay. So we will start. I'm just gonna go to my board mode and write the problem again. So this is P1 and I have here P2. They are separated by a distance r. So this distance is r. Okay. So if you will recall, the electric field of a dipole just given by P over 4 pi epsilon naught r cubed 2 cosine theta r hat plus sine theta theta hat. So this is the electric field of a dipole in spherical coordinates. You also have another form of this, which is the coordinate free form. So free from any coordinate system. But this is specifically the electric field of a dipole in spherical coordinates. So we will just use this one. Okay. For the first question, we are asked to find the torque on P2. So that's the first question, the torque on P2. Due to, of course, the electric field of P1. So we need now to set the electric field of P1. So the electric field of P1 will just be like this. By the way, theta here is measured from the z-axis. We will always assume that the direction of our dipole will be along the z-axis. So it's safe to assume that, that this direction here is the z-axis, say z1. And it's also safe to assume that this direction here is also the z-axis for the second dipole, say z2, that one. And then you can assume any direction. So I can assume that this direction is x1. I can assume that also this direction is x2. But actually, it doesn't matter what type of direction you assume. The important thing is, you need to assume that our dipole moment, P1 and P2, are pointing to the z-axis. Okay, so theta now is an angle directed with respect to the z-axis. So theta here is measured from the z-axis. Okay, so for the electric field of P1, it will just look like this. So we'll just replace theta by theta 1 and P by P1. At the location of Q, at the location of P2, with respect to the dipole P1, the location of P2 is actually at theta is equal to pi over 2. Theta is equal to pi over 2. So at theta is equal to pi over 2 at the location of P2, the electric field of P1 there at this point is given by this, for theta is equal to pi over 2. So you will have cosine of pi over 2 is 0, sine of pi over 2 is 1. So we have a theta hat direction. So we will have a P1 over 4 pi epsilon naught r cubed, and then the direction will be theta hat. So this is the electric field of P1 at this location. So take note, we measure, this should be theta 1 because the angle is with respect to the theta of P1. This is the z-axis. You measure theta from the z-axis from the North Pole to the South Pole. So the location of P2 is 90 degrees or pi over 2. So the theta hat direction, by the way, is just a line which is tangent to the circle here. So in this case, the theta hat direction for E1 is actually directed downwards. This is actually your E1 here. So that is actually the theta hat direction. And in our coordinate system, if we convert this theta hat into the x, y, and z axis, so we define this as our x1, and this is our z1 axis. So basically, the direction of E1 is negative z1. So I can actually write this as P1 over 4 pi epsilon naught r cubed negative z1 hat, because the positive z1 direction is upward with respect to P1. So we are using the coordinate system for P1. So that you will not be confused, I will just erase this. I will just use this coordinate system later. Okay. So for the torque on P1, or sorry, torque on P2, the torque exerted by 1 on 2, so it's just the dipole P2 crossed with the electric field of E1, the external electric field. So we cross this and P2. By the way, with respect to the coordinate system that we have assigned here, the P2 dipole moment vector is directed along x1. So we will have P2 x1 hat. So this is the dipole moment vector. With respect to the axis that we defined here, it's in the x1 direction. You cross it with E1, which is just this one, P1 over 4 pi epsilon naught r cubed negative z1 hat. So you will have x1 cross negative z1. So x cross z, that will actually give you negative y hat, negative y1, but there's a negative sign here, so that will actually give you positive y hat. So the torque now will be, oh, can you see it? P1 P2 over 4 pi, oh, you can't see it. Yun na lang. So P1 P2 over 4 pi epsilon naught r cubed, all of the constants, and then x1 hat cross negative z1 hat will give you positive y hat. So this actually doesn't matter, because we're just going to convert our answer with respect to the orientation here. So if this is the positive x-axis and upward is the positive z-axis, then where is the positive y-axis? So they all follow the right-hand rule. If this is the x, so this is the y, it's into the page, and this is z, upward. So this direction, positive y hat, is actually into the page. Oh, sorry, you can't see it again. So the positive y hat direction, this is the magnitude of the torque, and the direction is positive y hat, or in this case, into the page. So the torque on P2 due to the electric field of E1 is into the page. Into the page, so meaning it will rotate clockwise. So the rotation will be, since the torque is into the page, if the torque is into the page, the rotation is this, your fingers. So it's clockwise, meaning the dipole moment P2 will rotate in this direction, which makes sense because it will tend to align with the electric field at this location, which is directed downwards. So meaning your dipole moment will rotate so that it will align with E1, like that. So this is the torque on P2 due to the field of P1. So you do the same for the second question, the torque on P1. So for the torque on P1, we will try to find, this will now be our new axis. This will now be our Z2 axis. So this will be our X2 axis, meaning the Y2 axis will be into the page. So that is now our new axis. So I'm gonna erase this so that it will not be confusing. So that's the technique. You need to align your dipole moment along the z-axis. So this is the z-axis of the second dipole. Okay. So what is now the electric field of the dipole at the location of P1? So at the location of P1, this is the z-axis. So this is P2. What is this location with respect to P2? So this is the z-axis. So we measure, this is the positive z-axis, so measure the angle from this axis here. That's actually 180 degrees or pi. So theta is equal to pi. This is the location of P1 with respect to the dipole P2. So theta is equal to pi. So when theta is equal to pi, sine of pi is 0, cosine pi is -1, and you will get so you have 2 and then 4, cancel ang 2, so p over 2 na lang, p over 2 pi epsilon naught r cubed, and cosine pi is -1, so negative r hat. Okay, so the direction, what is this direction, negative r hat? So the negative r hat direction is actually, it's the radial direction, so it's towards the dipole. So negative r hat means the r hat direction is away from the dipole. We should put r2 here, r2. R2 is away from the dipole, so negative r2 means towards the dipole. So meaning the electric field of P2 at the location of P1 is actually in this direction. This is E2. That's the negative R2 direction. So I can actually write this in terms of the axis that I defined here. In terms of the Cartesian axis, I can actually write this as, or I can replace negative R2 hat by positive Z2. So I can replace this by positive Z2 hat. Okay. From our new axis here, I can now define the P1 vector as, this is directed upwards, and this is the positive x2 axis. So its direction will be negative x2 hat. So to solve for the torque on P1 due to torque exerted by dipole 2 on 1, it's just P1 cross P2. So you cross these two vectors, but you now use the Cartesian z. So you will have x cross z, and you will get negative y. There's a negative sign, so you have positive y. So you do that, and the answer that you will get is this: P1 P2 over 2 pi epsilon naught r cubed. The direction is y2 hat. Sorry, this should be y1, y2 hat. But in both of the cases, the y1 hat here and the y2 hat are both into the page. So these directions are into the page. So the torque on P1 is into the page, meaning the rotation is still clockwise, which makes sense because the electric field is here. The torque will align the dipole moment will try to align with the electric field. That is why it will rotate in a clockwise manner. So if you will notice, the two magnitudes are not the same, even though their directions are basically the same into the page. But their magnitudes, the magnitude of this is actually 1/4 and this is 1/2. So this is half as compared to the torque exerted by 2 on 1. So this is actually twice the torque. This torque here, the torque exerted by 2 on 1 is actually twice the torque exerted by 1 on 2. So meaning the rotation of dipole P1 will be much faster as compared to the rotation of the dipole P2. So again, they will both exert a torque on each other. Okay, so that is now the answer to example number 2. So let's now have another example, example number 3. So in this problem, you have a grounded conducting plane. So that is a plane. This is just the side view of the plane. So it looks like a line. And a distance z above the plane, you have a dipole with dipole moment P. We are always assuming here that unless it's given in the problem, we will assume that P has a constant is constant in magnitude. And then you are asked to find the torque on the dipole because of the grounded conducting plane. So find the torque on the dipole, and if the dipole is free to rotate, in what orientation will it come to rest? Okay. Oh, sorry. So let's now try to solve this problem. So I'm just going to go again to my board mode. So this is our grounded conducting plane. And our dipole is here. Dipole moment P. Sorry, you can see it. And it's the distance between the dipole, the perpendicular. This is the perpendicular distance, no? Between the dipole and the plane is z. So how do we solve this type of problem? You may already have an idea here, on how to solve this, because we encountered a similar thing before. So in our previous chapter, we have discussed a grounded conducting plane and then a point charge above it. And what we did there, we used the method of images. And we can also do the same because this is just a point dipole. So we can add a distance z below the plane. Since we are just trying to find or solving the region above the plane, so we can use an image, a dipole, a distance z below the plane. So this is now our image dipole. It will have a dipole moment Pi. So the magnitude of these two dipoles are the same. The magnitude of P and Pi are the same. So P is just equal to Pi, their magnitudes, but their directions are different. Take note that a dipole is pointing from a negative to a positive side. So meaning, to cancel this out, this should be a positive, this should be a negative. Hence, the direction of our image dipole is in this direction. So that this negative will cancel with that, positive will cancel with positive head, will cancel with the negative tail of this image dipole here. So this is method of images. We use method of images here to solve for the torque on this dipole here. So this is a grounded conducting plane, meaning the potential at this surface is 0. So if you have two dipoles oriented in this direction, then the region in between them will have 0 potential. So basically just similar with what we did in the classic image problem. Okay, so what we will do here is we will rotate our axis. So as I've told you earlier, it's easier to orient your dipole moment along the z-axis. So we will call this direction as our z-axis. This will be the z-axis, our new z-axis. So this is our new axis. I'm just gonna rotate that. So if you will notice, if this is now our new z-axis, this is now the origin, the location of the image dipole, the origin, then you will see that the image dipole, this is now our image dipole, right? I just rotated this coordinate system like that. Okay, so in this rotated coordinate system, where is now our original dipole? By the way, in our original problem, we're actually given an angle here. This angle here is actually theta. So meaning, by the law of if this is theta, then this angle should also be theta due to symmetry. Meaning, if the location of the dipole, original dipole P, is in this direction, then this angle is theta, meaning the orientation of our dipole will look like this. And this angle here is the angle theta. This is our dipole now. And the distance between these two dipoles, dipole and this dipole, this distance is 2z. Okay. So in this case, we can always write dipole as a function of theta and phi. So sorry, theta and r rather. So I can actually let this as the r hat the direction, and perpendicular to this, of course, is the theta hat direction, such that our dipole will now have an r component and a theta component. So take note, we are assuming here that our dipole is along its own z-axis. So it has an angle theta with respect to z. The z-axis always has an angle of theta with respect to the r-axis. Okay, so with that, if you'll notice here, I'm just gonna rewrite our dipole. This is our dipole, and these are its own coordinate system. The r hat coordinate system of the dipole. This is the theta hat coordinate of the dipole. This is 90 degrees, and this angle here is theta. So from this orientation, we see that P cosine theta r hat, that is the r direction. This is P cosine theta r hat, that is the r component, and its theta component will be P sine theta, P sine theta theta. Okay. So this will be our dipole now. So we're trying to find the torque on this dipole, and the torque on this dipole will be due to the electric field of this dipole here. So we now replace the grounded conducting plane by an image dipole. So the electric field of this dipole will exert a torque on this dipole here. So the electric field of our image dipole E sub I will be P over 4 pi epsilon naught. We use the same formula. So the r, the distance here is 2z, so it's now 2z cube. This should be, supposedly this is r cube. And we have 2 cosine theta r hat plus sine theta theta hat. So this is the electric field of our dipole. Okay, so at the location of P, actually theta, so we don't have an exact answer. So what we need to do is just to cross this 2 to solve for the torque. So the torque on the dipole P is just the dipole moment of P crossed with the external electric field, which is due to the image dipole. So we cross these 2, cross product. So the rules of cross product, the cross product of a unit vector with itself is 0. So meaning r hat cross r hat is 0, theta hat cross theta hat is 0. And so the terms that will survive in the cross product will be r hat cross theta hat, which will give you phi hat. And the reverse, theta hat cross r hat, that will give you negative phi hat. So you do that, you cross these 2, I will leave the cross product to you. And you will get this answer, p squared sine theta. So take note, the image dipole has the same magnitude, p, with our original dipole, p. Sine 2 theta over 64 pi epsilon naught g cube. And the direction of this is negative phi hat. So the magnitude of the torque is this one. The direction is negative phi hat. So if this is the r direction, this is the theta direction, the phi hat direction is actually into the page. So the phi, from this coordinate that we have established, the phi hat direction is into the page, meaning the negative phi hat, this direction will be out of the page. So out of the page. Okay, but we cannot say automatically that the direction of the torque on this dipole is automatically out of the page, because there's the angle theta here is still variable. Now, what will happen if theta is between 0 to 90 degrees? If theta is from 0 to pi over 2. So such that your dipole is oriented in this manner, where the angle is from 0 to pi over 2. So when theta is from 0 to pi over 2, this term here, sine 2 theta, will actually be positive. So this whole term here will be positive, so the direction is negative phi hat. So the direction will be out of the page. So the direction of the torque will be out of the page. So the torque will be out of the page, meaning the dipole will rotate counterclockwise. So this dipole will rotate counterclockwise, and if it's free to rotate, its final orientation will be upward. So the final orientation of this dipole will be upward, since it will rotate counterclockwise due to the torque being out of the page. So this will be the final orientation of your dipole. It will be upward. It will rotate upward and then stay that way in equilibrium. Now, in another scenario, when theta is between 90 degrees or pi over 2 to pi, this term here, sine, sorry, this should be sine, this is sine 2 theta. Sorry. The sine 2 theta term is actually negative. So this is now negative. There's a negative sign. So the final direction of the torque will be positive phi hat. And the positive phi hat direction will be into the page. So in this case, into the page. The direction of the torque will be into the page. So that scenario will happen when your torque is oriented with an angle of like that. So it's theta. Take note, in this scenario, this is the orientation of your P in this scenario. its theta is actually greater than 90 degrees, from 90 degrees to 180 degrees. So in this scenario, in this condition, when theta is in that condition, the torque will be into the page. So meaning, if it's into the page, the torque is into the page, the dipole will rotate in a clockwise manner. So if it will rotate in a clockwise manner, so it will rotate clockwise, like that. So its final orientation will be downwards. So there are two cases again here, depending on the initial value of your theta. If theta is from 0 to 90 degrees, then the torque is out of the page and it will rotate counterclockwise, and the final orientation of your dipole will be upward, will be directed up. But in the scenario where the angle theta is between 90 degrees to 180 degrees, then the torque will be into the page. And hence, the final direction of the dipole will be downward. Okay, so that is for example number 3. So let's now go to the last example for this lesson. So we have a dipole and a point charge. So we actually have solved a similar problem in the previous lesson. We have a dipole, which is the neutral atom, which was polarized. It became a dipole. It has a dipole moment, and it's a distance r from the point charge. But in that example, the direction of the dipole moment of the polarized atom was actually in the line connecting these two. But in this example, it's now much general. It has an angle of theta with respect to the line connecting the point charge and the point dipole. Okay. So you are asked to find the force on the dipole. So meaning the force exerted by the electric field of the point charge on the dipole. And for the second problem, find the force on the point charge, meaning this is now the force exerted by the electric field of the dipole on the point charge. And by virtue of Newton's third law of motion for force, that these two forces must be equal in magnitude but opposite in direction, or they must be the negative of each other, or they must be anti-parallel. Okay, so let's try first to solve for the force exerted by letter A, the force on the dipole. Oh, sorry. So I'm just gonna go to my board mode here. Okay, so let's first try to solve for letter A, the force on the dipole. The force on a dipole due to an external electric field is given by this equation. The dipole moment, that with the del operator acting on the electric field. So the electric field here is the electric field of a point charge. So we already know the electric field of a point charge. We already learned that in basic electricity or basic electrostatics. So it's just 1 over 4 pi epsilon naught q over r squared, and its direction is r hat. So this electric field is actually in spherical coordinates, meaning we need to write our operators here in terms of spherical coordinate. So as we have encountered earlier, we can actually write our P, dipole moment, as a function of, or in terms of the r and theta components. So we can write it as P cosine theta r hat plus P sine theta theta hat. So you can imagine it as like this. This is the r hat direction, this is the theta hat unit vector. and your dipole is in this direction. It's in the r theta plane, and this is an angle theta. So the p cosine theta is the r component, and p sine theta is the theta hat component. So this angle is actually pi over 2 minus theta. So we can also write this in coordinate free form, since from here we see that p cosine theta, this looks like a dot product between the p vector and a unit vector. And here the unit vector that we will choose is r hat. So this is actually p dot r hat. P cosine theta is actually dot product between p dot r hat. So from the definition of dot product. And this is actually the dot product between p and theta hat. Take note that the angle between p and theta hat is pi over 2 minus theta. And cosine of pi over 2 minus theta, if you will recall in your elementary trigonometry, the cosine of pi over 2 minus theta, that is equal to sine theta. Basically, p sine theta is just the dot product of the p vector and the theta hat vector. Okay, so that is our p, and this is our e. We now have one operator left, the del operator. So since we are working in spherical coordinates, it is advisable to write our del operator in terms of spherical coordinates. So that is partial with respect to r hat, plus 1 over r, partial with respect to theta hat, plus 1 over r sine theta, partial with respect to theta, phi. Partial with respect to phi hat. This is the del operator in spherical coordinates. So what is now the operator p dot del? So what is p dot del, this operator here? So it's just a dot product of these two vectors. So that product, meaning you just multiply the same components, r hat dot r hat, theta hat dot theta hat. There is no p hat component for the dipole moment, so it will be 0. So just dot the same component, multiply the same components. So you will have, I'm just going to use the coordinate free form. So p dot r hat, and then partial with respect to r. So take note, the order is important here. You first write the component of p and then the component of the del operator, not the reverse, because if you do the reverse, that's actually the divergence. So that's the multiplication of the r components, and then for the theta components, you have p dot theta hat, then multiplied by this, so over r, partial with respect to theta. So that is the p dot del operator, and this operator will act on our electric field here. Okay, so meaning, going back, the force now is just this operator acting on this vector E here. So the only terms, or the terms that this operator will act, will just be these two terms here, 1 over r squared and r hat, or r hat over r squared. So essentially, if we take out all the constants, you will have q over 4 pi epsilon naught, that is the common term for all, and then you will have p dot r hat, partial with respect to r, of r hat over r squared, that term where the operator acts, plus you have p dot theta hat over r, partial with respect to theta, of r hat over r squared. Okay, so this is actually two terms, or two differentials, because this is differential of a quotient, or you can think of this as differential of a product, the product of 1 over r squared and r hat. But the derivative of r hat with respect to r is actually 0. So the only term that survives will be the differential of 1 over r squared with respect to r. And this term will actually give you negative 2 over r cubed r hat. Similarly, this will also have two terms, the differential with respect to theta of 1 over r squared plus the differential of r hat with respect to theta. But the differential of 1 over r squared with respect to theta is 0, meaning the only term here with the differential with respect to theta is r hat. So you need to review the review lesson in chapter 0 here on about the unit vectors and their derivatives. So the derivative of r hat with respect, so the only term that will survive here is the derivative of r hat with respect to theta. And the answer of that is actually theta hat. So you need to review this lesson so that you can understand this part of the solution much better. Okay. So what do we have now? Sorry, I forgot to write the 1 over r squared. Okay, so there's a 1 over r squared here times there's a 1 over r, so r cubed. Here you have r cubed, so you can actually factor out the r cubed. So where will I put this now? Here na lang. So the force will now be q over 4 pi epsilon naught r cubed, and then there will be negative 2 p dot r hat, so p dot r hat plus p dot theta hat. Okay, so from here we see that p dot theta hat is actually just p, and we transpose this to the other side of the equation. So that's actually p dot theta hat is actually just p minus p dot r. So if you will see here, p dot theta hat just actually p minus p dot r hat. So you transpose in the other side of the equation. You replace this by this one, p minus p dot r hat, and you will get the force on the dipole as q over 4 pi epsilon naught r cubed. Can you see it? I'm just gonna erase myself that you can see it. Okay, will be p minus 3 p dot r hat. Oh, okay. So this is now the force on the dipole due to the electric field of the point charge. Okay. So for letter B, you just need to use the electric field of a dipole. So the electric field dipole, you can use the coordinate free form of the electric field of the dipole and just multiply it by Q. So this is the force on the dipole, force on P. For letter B, the force on Q, the point charge, it's just Q times the electric field of the dipole, the electric field of P. So you can use the coordinate free form of the electric field dipole, multiply it by Q. And that's it. And you will expect that the result that you will get will be the negative of the force on the dipole. The negative of this. So the negative of this is just the reverse of these two terms inside the parenthesis here. So I will leave that example to you. Okay. So basically, that is the answer for example number 4. So this is the last example, and that's the end, basically the end of this lesson. So for the next lesson, we will be investigating about how polarization induces dipoles and in turn bound charges on your dielectric. I will see you again in the next lesson.